Today I'll just show you guys the exponential distribution and its memoryless property. So we say a continuous random variable x is exponentially distributed with parameter lambda if it has the following probability density function, where f of x equals lambda times e to the negative lambda x for x greater than or equal to 0 and 0 otherwise, right? And we also need lambda greater than 0. So I'll just quickly draw your attention to two things here. Firstly, we really are equal to 0, right? For x less than 0, our PDF doesn't just disappear. And secondly, you should know that this distribution is usually used to model the time it takes for something to happen. So for example, the time it takes for a light bulb to burn out, or the time it takes for a customer to arrive at a store. So now while I will show you the CDF of this distribution in just a moment, I'd like you to pause the video here and try to find it yourself. Use the integration. It does have a closed form. It's pretty straightforward to find. Give that a shot. So here's the CDF of the exponential distribution as promised, where big F of x equals 1 minus e to the negative lambda x for x greater than or equal to 0 and 0 everywhere else. And, I will draw to your attention here again, right, that all the CDFs as x goes to infinity approach 1, right? You see this guy here. And also, just like our PDF, right, below 0, we are equal to 0. Yeah, now case 1 is pretty easy to see here. But to be clear, what I mean by no values below 0 or in the distribution is that below 0, right, all of our PDF values are 0, right? So we have no non-zero values below 0. In other words, all of our non-zero values are when x is greater than 0, greater than or equal to 0, sorry. Now for our second case, right, when x is greater than or equal to 0, all we do here is really integrate using the PDF from earlier. I even took the constant out here to make that extra clear. So this should be pretty standard for you guys, like this step here, as well as the rest. But either way, right, you should see that our CDF goes to 1 as x goes to infinity, and that it's 0 for x less than 0, right? You don't need to be able to graph it in your mind. But if you just, do the limit as x goes to infinity, or you plug in x 0, right, and you'll see that we do fit the properties needed for CDF. So next I'll walk you through how to find the expectation, the variance, and the MGF of this distribution. So, if you'd like to give those a shot before I spoil them, just pause the video here. And otherwise, we'll jump right into it. The expectation is pretty beautiful here. And now you'll know why I highlighted where 1 over lambda was on the PDF earlier. Rewind if you'd like to see that again. But, essentially up here, all I'm doing is just restating the definition of expectation. Right here, this is just our PDF. And again, down here, the integral is pretty straightforward, but we're integrating by parts, so I will walk you through this. All I'm doing is letting u equal to x and dv equal to e to the negative lambda x, right? So that's how we get this part here. And you'll see as if you plug in your, if you do your limit as x goes to infinity, right? Obviously, this overpowers my x, so that's how we get 0. And then equivalently, in the other case, right, this is 1, and then this is 0, so we have 0. This whole integral is 0. And up here, right, we saw this previously. All you're doing, right, is you're just boom, boom, boom. This is pretty standard e to the negative kx integral after that, right? And then it's just algebra. The variance of our distribution is 1 over lambda squared. And, up here, I'm just restating the variance, the definition of variance. And then here, right, I just do, in this part, I'm just doing integration by parts like we did for expectation, right? But in this case, I just let u equal to x squared and dv equal to e to the negative lambda x dx this time. So all I've changed is my u, right? But my dv is the same, which is why it's so similar. And it's the same reason we get our 0, like we did last time. And then in this second part for our second integral, right, first I pop the 2 out, That's where this 2 comes from. I pop the constant out. And then I'm just multiplying by 1, right? 1 over lambda times lambda is 1. And you'll see, wait a minute, isn't that our expectation, right? So remember, our expectation is 1 over lambda. So that's how we get this guy. And then it's just algebra. Now, while our MGF might be a bit easier to derive than our variance, we do have to be careful with the limit at some point in here. So I will walk you through this just quickly right now. So up here, I'm just restating the definition of our MGF, as usual. And here, I'm just restating our PDF. So there's nothing new up here. You can ignore this. And down here, right, all I'm doing is taking my lambda out and simplifying my e's. So there's nothing new here. And this, follows directly from the way you integrate with exponentials. But now I'm taking the limit as x goes to infinity, right, down here. And this is where you need to be careful, as it does depend on t being less than lambda. As I've noted here, like all MGFs, depend on something similar to this. And then after that, right, all we do is multiply by -1. We flip the bottom, and then we have our MGF. But really do note this point here where, if t is greater than or equal to lambda, our limit is undefined. So this part may seem very counterintuitive at first, but it's actually a very useful property of the exponential distribution, and it's not that hard to prove. The main point here is that, if an event's time follows exponential lambda, let's say a bus's arrival time, and you've already waited 5 minutes for the bus to arrive, right? It's as likely to arrive in the next 5 as if you had just started waiting. So it's like it forgot that you had waited 5 minutes already, right? It's like those points in the bank, it just forgot them, which is where the name Memoryless comes from. So let's look at the proof here, right? We can simplify this part, this guy to this guy, because s plus t is greater than s, right? So if x is greater than s plus t, we know x is greater than s. And from there, we just use the definition of the CDF and do some algebra, right? Remember that, just to be clear about what I mean by the definition of the CDF, remember that when we want p of x greater than s plus t, right? Due to the properties of probability, we just do 1 minus p of x less than s plus t, which is our CDF, this guy, right? Since we're in the continuous world. So that's the same reason this guy equals this guy. You can prove that yourself, it's just a bit of subtraction. But yeah, so in a moment, I'll let you take a look at the practice questions I've written up. But for now, take as long as you need to make sure you understand this slide, despite how counterintuitive it may be. Here I've given you some practice problems of different difficulties, and I do highly encourage you to give these a shot. But yeah, anyways, thanks for listening. Feel free to ask your questions in the comment below. And please do let me know if I made any mistakes at any point in this video. I'll see you guys next time.